So essentially, the van der Waals forces. Let's say we have an atom. All right. So the atom we have our nucleus, right, and we have nucleus, whole bunch of positive charges in it, and then the electrons form a cloud around it, right? And so when you have two of these next to each other, you can get some spontaneous shift in the arrangement of the electrons around the atom, right? So, for instance, let's say that in this atom on the left here, we get a separation of charges, right? So maybe the density of electrons shifts towards the right hand side of this figure, and then the nucleus shifts towards the left hand side, right? So you get a slight positive and a slight negative charge. So something like this, right? So you have uneven distribution of charges. You have the same amount of charge, it's just distributed differently, right? So this creates a slight positive charge and a slight negative charge on your atom, right? Now, because the left atom is in close proximity to the right atom, this spontaneous redistribution of charge will actually influence the other atom as well, right? So when this other atom is brought nearby, what's going to end up happening is that the positive nucleus will be attracted towards the electrons on the other atom. So the other atom will experience something like this. The nucleus, because it's positively charged, gets attracted towards the slightly negative end of the left atom, and the electrons get repelled away. So the electrons end up over here. Okay, and so with this atom, you get also a slight positive and a slight negative charge, right? So essentially, what we've created here is two temporary dipoles, right? So dipole meaning we have a unequal distribution of positive and negative charges. We have a positive pole and a negative pole. That's what a dipole is, right? And so we actually get a force of attraction between the slight negative and the slight positive charge. Okay, and that's what a van der Waals force is. It's that force of attraction between the slightly negative end of one atom and the slightly positive end of another atom. All right. Now this is super weak because this charge separation is actually not quite. It's not very strong, right? So it's very easy to break, and this force of attraction is only present when these atoms are pretty close together. So as soon as these atoms are moved further apart, it doesn't. There isn't enough attraction between these two to create this. It's not even a bond, but it does sort of keep these atoms sort of locked together. But I don't know, Samarth, what do you think about that little quick explanation? Okay, so today is going to be all about rational functions, and specifically vertical and horizontal asymptotes. Okay, so I mean, in advanced functions, you definitely would have seen I don't know, functions that look like this, where we have, let's say, two pieces of a function. Maybe it does something like this. Maybe something like this. All right, and basically in advanced functions, we talked about, okay, let's find where the vertical asymptotes are. Let's figure out what the horizontal asymptote is. Let's find some intercepts if we have it. And then a lot of the time that you spent in that chapter of advanced functions was basically revolved around how to graph this thing, okay? Now, we're going to take that a step further in calculus. Of course, we have to. Today is going to be a little bit of review of what you would have done in advanced functions, but then we're also going to bring in limits into this, and that actually changes it up a little bit. Now, I know when I taught my advanced functions class, I showed them a little bit of limits. Well, without calling it a limit. In advanced functions, you probably talked a lot about end behaviors, and you might have also talked about vertical asymptote behaviors. And that's what we're going to kind of tie into this, or what we're going to discuss today, but we're going to do so in a much more formal and rigorous way. Okay, so let's get into it. Actually, before that, have you guys ever chatted about? Have you guys ever talked about what an oblique asymptote is? So something like this, like a slanted asymptote. Okay, so yeah, just a little bit of review. Again, you guys seem pretty good at recalling this stuff already, but essentially a rational function is any function of the form p of x over q of x, where p and q are both polynomial functions. Okay, so any rational function can be expressed of the form p of x over q of x. Okay. And so let's first do some just basic examples. Let's try to figure out how to find what I like to call vertical asymptote behaviors, or maybe a little bit more specifically, the behaviors of the function near the vertical asymptotes. Okay, and so I have this function here. So f of x equals x over x squared plus x minus 2. Okay. So my first step here is let's just find our vertical asymptotes, okay? And so to find the vertical asymptotes, what we're going to be doing is we're going to be trying to figure out all the values of x that make the denominator equal to 0, okay? So essentially what we're doing is we're trying to figure out, okay, x squared plus x minus 2, we want to know when that's equal to 0. So it's a factoring question, basically, all right? So in this question, we know that we have to multiply to -2 and add to +1. So that is just +2 minus 1. So we get x plus 2, x minus 1 equals 0, which means that we have a vertical asymptote at x equals 1 and at x equals -2. So we have two vertical asymptotes in this example. Okay, and so our job here is to figure out what is the graph doing near the vertical asymptotes, right? We know it'll kind of like the way that vertical asymptotes behave. It seems like the function either shoots up to positive infinity or it shoots down to negative infinity. Okay, and so what we're going to do is we're going to kind of formalize the way that we figure out what the function is doing near the vertical asymptote. Okay, so the way that we do that to find the vertical asymptote behaviors is we're going to consider several limits here. Okay, in fact, we're going to consider two limits for each of our vertical asymptotes. So in this example, we have two VAs. We're going to consider four separate behaviors. Okay, so we want to figure out what is the limit of the function f of x when x is getting really, really close to, so I'm going to pick 1, so my VA 1. So what is the function doing when the x values are getting really, really close to 1 from the negative side, right? Meaning I'm approaching 1 from the left-hand side of 1. So the values are like 0.9, 0.99, 0.999, so on, right? I'm also going to try to determine what's going on with my function when I approach 1, but now from the positive side. So 1.1, 1.01, 1.001 would be kind of the test points that I'm considering here. Okay. So I want to know what both of these functions are doing, because in order eventually next week on Monday, what we're going to start to do is start to graph these things, right? So what these two limits will allow us to do is figure out what the function is doing near the vertical asymptote so that we can make a more accurate sketch of it. Okay. The way that we find these, we can actually use test points to figure out what these are. Okay. So this is actually probably the way that you would have done it in advanced functions. So you could do something like, oh, I'm going to evaluate my function at 0.9. And then maybe evaluate my function at 0.999, right? So you're getting progressively closer to 1, but the values are still smaller than 1, right? Similarly, we could evaluate this limit by taking test points. So we start at 1.1, and then we get closer, 1.001. Okay. So that's one way of doing it. So let's see what that'll give us, okay, when we plug these in. So if I plug in 0.99 or 0.9 into my function, so 0.9. Actually, let me do this in Wolfram Alpha so I don't have to keep typing it into my calculator a whole bunch of times. So I have x over x squared plus x minus 2 when x is equal to 0.9. So when x is equal to 0.9, I get negative 3.10345. And then how about when x is equal to 0.99? 0.999. Let's see what we get. So when you plug in 0.999, we get negative 333.111. So based off those two values, as I get closer and closer to x is equal to 1, it looks as though my function is getting increasingly more negative. And so we say that the limit as x approaches 1 from the negative side is equal to negative infinity, because my values just get continually smaller. Okay. Okay. Another way of actually seeing that, just because, you know, plugging in test points is fine. It gets you the right answer, but it's a little bit time consuming because you have to sit there on your calculator and kind of punch in a whole bunch of numbers, right? It's kind of annoying to do, okay? The way that you could do this, kind of the shortcut to this, is you look at f of x and you write it so that everything is factored, right? So I have x over x plus 2, x minus 1, okay? Now what we can do is we can imagine plugging in a value very, very close to 1, but just a little bit less than 1. Okay, so imagine plugging in a value just below 1. So like we're imagining plugging in 0.999, right? Well, if we do that, what we're going to find out is that, okay, well, we put in 0.999 for x, so we get, in our numerator, we'll get a positive number, right? Because 0.999 is positive. And then 0.999 plus 2, that's also going to be a positive number. And then we have 0.999 minus 1. Uh-oh, that's going to be a negative number, right? So if we were to plug that number in, we would get a positive divided by a positive times a negative. That answer ends up being negative. And if we look up here, we notice that our function goes off to negative infinity. So it matches up with it, right? Now we can imagine, okay, what would happen if we plugged in a number just above 1? So just above 1. So say 1.001. Now we could do this on Wolfram Alpha. We could plug in our test points, type it into your calculator and get a value. Or we could do this kind of hand-wavy approximate way just to see what we'll get, right? So again, 1.001 into this function. Well, my numerator is still going to be positive. If I do 1.001 plus 2, well, that's a positive. 1.001 minus 1, oh, that'll be a positive as well, right? And so I get a positive divided by a positive times a positive. That answer is positive. I can come up here to my limit, and I note that the limit goes off to positive infinity when I do that. Okay, so I don't even have to compute test points. I can just sort of do this off the cuff. Okay, it's a little bit quicker that way. So yeah, quick way to evaluate limits. Any questions about the end behaviors near that function, near that vertical asymptote, or are we pretty good? So we've only dealt with as x approaches 1. Now let's figure out what's going to happen when x is approaching... so we also have another vertical asymptote, right? Let's figure out what's happening when x is approaching -2. So I'll just move this over a little bit here, just give myself some more room. Now let's figure out the other set of vertical asymptote behaviors. So the limit as x approaches -2 from below, and the limit as x approaches -2 from above. Okay. And so let's do the same kind of idea here. Okay. So again, we could do this with test points, right? It's time consuming, but we could do it. Or we can kind of use this sort of hypothetical, we imagine plugging in a value, and that's going to be a little bit easier. Okay. So imagine that we plug in, so for the first one here, for the first end behavior here, what we're going to do is we're going to imagine plugging in, say, -2.001. So something just a little bit more negative than -2, right? Well, if we do that into our function here, well, x is going to be negative, right? So we'll have a negative over, and then we have -2.001 plus 2. Well, that'll still be negative. And then we'll have -2.001 minus 1. So that'll be negative as well. So we have a negative divided by a negative times a negative. So it's a negative over a positive, which is a negative. Okay, so this function, -2 from below, will go off to -infinity. Okay. You can do the exact same thing, plug in test points here, but we would imagine plugging in something like -1.99, let's say. Okay. Now, if we were to do that, we would get, so -1.99. Well, x is negative, so our numerator would be negative. And then we would have -1.99 plus 2, so that's going to be slightly positive, very slightly positive. And then -1.99 minus 1, that'll definitely be negative. Okay, so we have a negative divided by a positive times a negative. That whole thing will be positive. So when we go from negative to above, we're going to get positive infinity. That's what our function is going to do. Okay. Now, you might be wondering, okay, why the heck are we doing all of this work, right? So we found a whole bunch of behaviors of our function, right? So limit of f of x as x approaches 1 from below is -infinity. From above is positive infinity, and then we found -infinity and positive infinity for the other asymptote, right? And so let's see the sketch of what this thing will look like. So here, I can probably expand this out a little bit here. That's not bad. So in the corner of the screen here, we can see what the function looks like. Okay, so let's kind of take a look at what's happening here. So let's take a look at -2 first. So when we're a little bit more negative than -2 here, here, where am I? Sorry, I'm just trying to, here, let me use Desmos. Desmos is probably a little bit easier here. Whoops, that's not. There we go. Here, I'll make it so that you guys can see. So what I'm going to do is I'm going to plot this. So x over x squared plus x minus 2. And let's just see that what I've kind of been saying kind of matches up here, right? So the end behaviors that I had, I said that as x approaches -1, or sorry, as x approaches 1 from below, this function should go off to -infinity. And we can definitely see that, right? We can see that the values get increasingly more negative. When f of x, or when x approaches 1 from above, we can see that f of x gets increasingly larger, right? Now, if we look at -2, if we approach -2 from the negative side, we can see that we go off to -infinity. That's what we said. And as we approach -2 from the positive side, we can see that we shoot off to positive infinity, okay? And so the end behaviors, or sorry, the behaviors of our function near the vertical asymptote basically describes what the function is doing at these points where the function is either getting really, really, really big or really, really, really small. And we're able to predict what the function will do at those values of x, okay? So is that clear? I'm sure this is something you guys have kind of seen before, but is there anything that's kind of not making sense here, or are we all pretty good? Okay, so I think that's a pretty good exercise for discussing what's happening with the vertical asymptotes. But now let's... hey, Michael, you want to mute your microphone? Let's figure out what's happening for the horizontal asymptotes. Okay, so for the horizontal asymptotes, what we're going to be discussing is the limit as x approaches infinity, or the limit as x approaches -infinity of our function. Because for the horizontal asymptotes, we want to know what's happening at very, very large x values or very, very small x values, okay? And so there's kind of a trick for evaluating these limits, and we'll see that in these examples here, okay? The trick that we use is we divide by the highest power that's present in the expression, okay? So let's see how that's done here, all right? So I need to evaluate the limit as x approaches infinity of 2x minus 3 over x plus 1, okay? So the limit x approaches infinity, 2x minus 3 over x plus 1, okay? So the trick that we're going to do here is we're going to divide by the highest, or divide by the term with the highest degree, okay? So in this case, we can see that, well, two terms have the highest power, right? The highest power here is just x to the power of 1. Okay, so x to the power of 1 is our highest power, okay? And so what we're going to do here is we're going to divide everything. We're basically going to like multiply by 1 over x in both the numerator and the denominator, okay? And we'll see why we're doing this in a second. Like right now it just seems kind of random why we're trying to do this, but it'll make sense in a second here, okay? So if I multiply both the numerator and the denominator by 1 over x, I'm not changing the function at all. And so I get the limit as x goes to infinity of 2 minus 3 over x over 1 plus 1 over x. Okay? And so now we can use a whole bunch of our limit rules, right? I'm dividing one thing by another thing. So what I can do is I can imagine this as I'm taking the limit of my numerator, so 2 minus 3 over x, and I'm dividing it by the limit of my denominator. Okay, so these are all the rules that we learned back in chapter 1, right? Our limit properties. Okay. And then I can even sort of, because I'm taking the limit of this entire thing, I'm taking the limit of the entire numerator and the entire denominator, what I can do is I can imagine taking the limit of each piece separately, right? And if you notice here, I'll end up with, so the limit as x approaches infinity of 2, well, that's the limit of a constant. That's just going to be 2, right? So this thing is going to equal to 2 minus the limit as x approaches infinity of 3 over x over 1 plus the limit as x approaches infinity of 1 over x. Okay. Now looking at these two expressions here, when x gets really large, like imagine x being 1,000, right? Well, 3 divided by 1,000 is going to be a really small number. And so this limit here just evaluates to 0. And the limit in the denominator also just evaluates to 0. And so what this means is that when our function approaches, or when x approaches positive infinity, our function is actually approaching 2 over 1, which is just equal to 2. Okay. And so that's the method that we use to evaluate limits at infinity. Okay. We divide through by the highest power, we simplify, and then we recognize that the limit of something over x is just equal to 0. Okay. Let's try another example. Same idea here, same setup, right? But this time we notice that the highest power is x squared, right? And so what we're going to do here is divide everything in both our numerator and our denominator by x squared to see what we get. Okay, so we get the limit as x approaches negative infinity of 1 over x in my numerator, and then I'll have I'll move that bar down a little bit. And then I'll have 1 plus 1 over x squared in my denominator. Okay. Now, even though notice here I'm taking the limit as x approaches negative infinity, really it's still a big negative number, right? And so I'm imagining plugging in a very large negative number into both the numerator and the denominator here. Okay. Well, if I throw it into if I put a really big negative number into 1 over x, the number I get will be negative, right? But it will be very close to 0, right? Like imagine typing it into your calculator. Let's do, say, 1 over negative 1,000 or something like that, right? We're going to get a number that's extremely or pretty close to 0, right? But it's still going to be slightly negative. Right, so it's still going to maintain it's still going to be a negative number, right? Now, so that means this thing will be very slightly negative, right? So it'll be approximately 0, but it'll be 0 and still a little bit negative, okay? And similarly, if we plug in a negative number into 1 over x squared, well, the square just gets rid of the fact that it's negative, right? So we're really just getting 1 over a big number, which is just going to be 0, but it's going to be slightly positive still, right? So this thing is going to be approximately 0, but it's still going to be positive, okay? And so this entire thing, what's going to end up happening is when we take the limit as x approaches negative infinity, it's kind of like I have something that's very slightly negative in my numerator, but still pretty close to 0, pretty much 0. Over 1 plus, something really close to 0, but slightly positive, okay? And so hopefully you'll be able to imagine this. Basically what we're going to end up getting is just 0, but the answer is still going to be slightly negative. So our final answer here we say is 0, but our answer is going to be slightly negative, okay? How are you guys with that? I know this is a new way of taking a limit, dividing by the highest power, but is it pretty self-explanatory? Any questions about that? Okay, so now let's deal with last example here, same idea. We're going to divide by the highest power, so we're going to divide by x squared here. And what we're going to end up getting is the limit as x approaches infinity of, so we'll have 2 plus 3 over x squared over 3 minus 1 over x plus 4 over x squared. Okay, so a lot of these things, because x is going to be a really big number, a lot of these things are just going to drop out to 0, right? And what's left over is just going to be 2 over 3. And that's the limit as x approaches infinity. Okay. Okay. And that's about it for taking limits. Hopefully that's not so bad. Okay. So let's kind of tie all this together now. I think I have 2 more quick examples, but we're going to kind of bridge everything together, right? So we're going to talk about both vertical and horizontal asymptotes in one example, okay? So here we have a function, 3x over x squared minus x minus 6, and we have to determine the equations of all horizontal or vertical asymptotes, okay? And then we'll illustrate the behavior of the graph as it approaches these asymptotes, okay? So yeah, let's give this a try. So we have f of x over 3x, f of x equals 3x over x squared minus x minus 6. The first thing that we want to do to figure out what our vertical asymptotes are is factor. Okay, so let's factor everything we see here. So f of x is 3x, can't do anything in the numerator. My denominator, I have to multiply to -6, and I have to add to -1. So that'll be -3 and +2. Okay. And so what this tells me is that I have 2 vertical asymptotes. I have a vertical asymptote at x equals -2 and x equals +3. Okay. And so now let's figure out our horizontal asymptotes. Okay. So I figured out the VAs using my factoring rules. My horizontal asymptotes, I want to know what's happening when I take the limit as x approaches infinity, and what's happening when I take the limit as x approaches -infinity. Okay. Okay. And so to do that, I'm going to go back to my function. And again, I'm going to divide by the highest power. Okay, so the highest power in this case is x squared is the highest power. And so when I do that, I'm going to get 3 over x over 1 minus 1 over x minus 6 over x squared. Okay. And then I can imagine plugging in a really big positive number into this. Okay, so what I'm going to see, is that this thing will effectively be 0, right? 0, but still a little bit positive. This thing is going to be 0, but still a little bit positive. This thing is going to be 0, but still a little bit positive, right? And so I'm going to get, essentially, my answer is going to be 0, right? And because I have 1 minus something that's basically 0 minus something that's basically 0, I'm going to get 0 over +1. So this whole thing should approach 0, but from a slightly positive side. Okay. Now, similarly, when we plug in -infinity into this, same idea. We're still going to divide by the highest power. So I'll have 3 over x over 1 minus 1 over x minus 6 over x squared. Same idea. Now, when I plug in a really, really big negative number into this, what I'm going to end up getting is I'm going to get, well, 3 over a really big negative number is basically going to be 0, but still a little bit negative, right? 1 over x is, again, going to be 0, but still a little bit negative. 0, bit negative. Again, 0, but a bit negative. Okay, so here I have something very, very close to 0, but slightly negative over basically 1, right? So this whole thing is going to be, it'll approach 0 from the negative side. Okay. And so what I can do is I can actually fill in some details here, right? So let's imagine starting to sketch this thing, okay? One thing that we'll start to see in this chapter is we're going to be doing a ton of these little sketches, all right? So here's my rough graph. It doesn't have to be a stellar sketch. In fact, like I encourage you to do like a really, really rough copy, and then what we're going to end up doing is just going into Desmos to check it anyway. So yeah, just a really, really rough idea. So let's start with this first part, okay? So here it's saying that as x approaches infinity, my y values are getting really, really close to 0, but they're staying positive. So my function is going to be doing something like this, right? My x values are getting really, really large, and my y values are getting close to 0, but they're staying positive. So they'll never dip below. They'll never be negative, okay? The other end behavior that I have here, so as x approaches negative infinity, y is approaching 0 from below. And so what that's going to look like, it's going to look something like this, okay? So I can already sort of see what my function will be doing at these very extreme values, okay? One thing I like to do personally, whenever I'm graphing a rational function like this, is I like to pencil in my VAs. I usually use red. So I have a VA at x equals -2, and I have a VA at x equals 3. Okay, and the VAs essentially represent, like, you cannot cross. We're not passing this line. Okay, but really I don't know, like, right now I don't know enough to say, okay, well, is my function going to go up like this, or is my function going to go down like this, right? Similarly, on the other side, I don't know where my function is going, right? I don't really have enough information to state where my function is going near these vertical asymptotes. I can kind of guess, right? Like, oh, well, this has to go up like this, so maybe something kind of down like that, but I don't actually know enough, okay? And that's why figuring out the behavior of the function near the vertical asymptote is actually so important, okay? And so what we actually have to do is we have to figure out the VA behaviors. And so to do that, again, we're taking the limit as x approaches -2 from the left side, the limit as x approaches -2 from the right side, limit x approaches 3 from the bottom side, and the limit as x approaches 3 from the positive side, okay, of our function f of x. All right. Okay, so again, I'm gonna use kind of like the trick, right? So imagine pick a number really, really close to -2, but still a little bit more negative. So -2.001, let's say. Imagine plugging in -1.999 here. Let's say 2.999 and 3.001. Okay, so now I'm going to imagine plugging into my factored version of my function here, okay? So if I plug in -2, or something very, very close to -2, my numerator will be negative. -2 minus 3, that'll be negative. And then -2.001 plus 2, that'll be still slightly negative. So I get a negative over a positive, which means my function is going to approach negative infinity. Okay. Let's imagine plugging in now -1.99. So my numerator will still be negative. -1.99 minus 3, that'll be negative. -1.999 plus 2, that'll be slightly positive now. So now I have a negative divided by a negative times a positive. That will actually be positive infinity. Okay. Now I can update this set of information, the new info that I found with these two limits, in my graph. Okay, so what this is saying is that as I approach my VA at -2, but from the more negative side, this thing will shoot down to negative infinity. Okay. Now, as I approach my vertical asymptote from the slightly more positive side, it'll shoot up to positive infinity. So right there, what this allows me to do is it allows me to kind of match it up here, right? I can notice that, oh, my function, I already have one piece of my function just from that set of information, right? And then I also know my function is going to do something, it'll have to shoot up here on the right-hand side of my VA at -2, okay? Now let's figure out what's going on near the other vertical asymptote, okay? So near +3. So again, I'm going to play the same game. I'm going to imagine putting 2.999 into our function here. So 3 times 2.999 is going to be a positive number. 2.999 minus 3, so that'll actually be slightly negative. Then 2.99 plus 2, that's going to be positive. So I have a positive divided by a negative times a positive. That whole thing is going to be negative. So negative infinity is what I get for that first behavior there. And let's imagine plugging in a number slightly above 3. So I get 3 times something slightly above 3. That's going to be positive. Divided by, I have 3.01001 minus 3. That's actually going to still be a little bit positive. And then 3.001 plus 2. That's going to be slightly positive. So when I do that, I get positive infinity. All right. And now that I found the VA behaviors, I can come back to my graph and I can start to update it a little bit more, right? So I know my graph is going to go, as I approach 3 from the negative side, I'm going to come down to negative infinity. And then if I look at the other side of my vertical asymptote, I'm shooting off to positive infinity, okay? So now I can just connect the dots, right? There's definitely a little bit more that we can do here, right? For instance, if I go back to my function, I actually notice that I have a x-intercept at x equals 0, so I can even include that if I want to. We'll talk a lot more about all the steps that we need to follow to really fully graph this thing on Monday. Right now we're just kind of getting an idea of what we can do with these rational functions, but we're going to have something that looks like this. Boom, and boom, okay. And of course we want to see how we did, right? So let's actually test to see how close we got. So we'll pop over to Desmos again, and we'll type this thing in. So I have 3x over x minus 3, x plus 2. Hey, not bad, pretty solid, right? Flipping back and forth. I think I did a pretty good job. Not bad. How are you guys with that example? Any questions about that? The curve sketching of this rational function? Are we doing pretty okay? Looks good. Cool. All good. Excellent. Okay. I think I just have one more example here, and then that's it for today. Okay. And actually, this is going to be an example of something with an oblique asymptote. So our goal here is we're going to figure out, how to graph the oblique asymptote, and then actually how to figure out how the function is approaching the oblique asymptote. That's probably the trickiest part of what we'll do today, but we'll talk about it, okay? So first things first, I have this function, f of x equals 2x squared plus 3x plus 1, minus 1 over x plus 1. So again, my first step is I factor everything, okay? So f of x equals, so factoring my numerator, let's see if I can factor it. So it has to multiply, I have to use decomposition here, multiplies to negative 2, adds to positive 3. Can't do it. I don't think I can do it. We can use Wolfram Alpha to try to factor this for us. So let's see what we get. 2x squared plus 3x minus 1. I don't think it's factorable. Oh no, it's factorable, but we get some weird roots, right? So again, basically we don't really care about what the roots are here. Like if we were graphing it, we would care because these would be our x-intercepts, but because neither of these are equal to x plus 1, we don't have to worry about any cancellations or anything like that. So that's really why we care about factoring. First, to get the x-intercepts. Second, to make sure that we're not canceling anything out, right? So in this case, I mean, we can factor, but it doesn't really help us, right? And so let's just leave our function as is for now, okay? What we can immediately see is we'll have a VA at x equals negative 1, okay? And so that's fine. We found the equation of our vertical asymptote. And if we wanted to, we could go through and do the same thing we did in the previous problem, right? We could figure out what our vertical asymptote behaviors are and all of that, but this question isn't asking for that, so we're not going to worry too much about it. But one thing we have to note, if we look at our numerator here, our numerator has a degree of 2, right? Because it's a quadratic polynomial in our numerator. Our denominator has a degree of 1, okay? Now, here's kind of a key, again, I'm sure you guys covered this in advanced functions, but in case you don't remember, if the degree of the numerator is exactly 1 larger, so the degree of the denominator plus 1, so it's exactly 1 bigger than the degree of the denominator, then the function has an oblique asymptote. Has an oblique asymptote. Okay. Now, to find the equation of the oblique asymptote, what we do is we take our numerator and we divide it by the denominator. Okay, so for that we have to use long division. So I'm sure you guys have been long dividing polynomials basically every day since you've learned it. So I'm sure this will be fine. But in case you haven't, let's practice this. So I set up my long division. I have 2x squared plus 3x minus 1 divided by x plus 1. Okay. So to long divide, we have to figure out, okay, how many times does x go into 2x squared? Well, it goes into it 2x times. And then I multiply, right? So 2x times x, that gets me 2x squared. 2x times 1, that gets me plus 2x. And I subtract. When I subtract, my 2x squareds will just cancel out. And I have 3x minus 2x, that's going to be equal to plus x. Okay. I bring down the negative 1. I don't have to fully long divide this thing. Okay. Basically, I'm going to stop after one more iteration here. So how many times does x go into x? Well, it goes into it 1 time. And then once I've done that step, I'm done. So as long as I have this linear piece in the as my quotient, I don't care what my remainder is. All I care about is that linear piece right at the top. That linear piece is the equation of my oblique asymptote. So therefore, my oblique asymptote, I just put OA just to make it easier. My oblique asymptote is given by y equals 2x plus 1. Okay. And so what I can do now is I can actually start sketching this function, right? I know where my vertical asymptote is. I know where my oblique asymptote is, and so I can do a quick little sketch. So I have a vertical asymptote at negative 1. Negative 1. And I have oblique asymptote at 2x plus 1. So my y-intercept is 1 and my slope is 2. So something like this. Again, it's a sketch. It doesn't have to be anything super precise here. So 2x plus 1. Okay. Now there are many ways of figuring out, okay, well, is my function going to do this and this, or is my function going to do this and this, right? It's kind of tough to know exactly based off the info that we currently have, right? What we could do is we could figure out the y-intercept. The y-intercept would tell us where we're going here, right? If we figured out the y-intercepts, we just plug in 0 for x, right? So we get 0 plus 0 minus 1, so that's negative 1 over 1, so that's just negative 1. So I know my y-intercept is down here, and that actually tells me that my function is going to be doing something like this. Okay. So I'll have another piece over here. All right. And one other kind of cool thing that you can do to figure out, okay, so notice here that the function will stay below my oblique asymptote, right? On the right-hand side. On the left-hand side, I can see that my function stays above the oblique asymptote. What you can also do is you can compare the value of the function and the value of the oblique asymptote at very large x values and very large negative x values, right? So what you can do is you can say, well, I want to know what my function is doing at 1,000. And I also want to know what 2x plus 1 is doing when x is equal to 1,000. Okay, so you can actually plug both of these in. The value of the function, I'll do that really quickly here. So let's type in our function here. X equals 1,000. I'm going to get a really large number. So I get 2,002,999. And when I evaluate my function, or my oblique asymptote, so my 2x plus 1 at x equals 1,000, I find a value of, wait, hold on. Something, I feel like something has gone wrong here. I haven't, oh, sorry, this isn't my function. This is just my numerator. Yeah, of course something has gone wrong. Divided by x plus 1. There we go, that's a bit better. I shouldn't get 2 million now. I should get something a little bit more reasonable. Can we approximate this? Yep, so 2001 is what my function is. Now, if I instead evaluate what my oblique asymptote is doing, I get a value of 2001 as well. I don't know if you noticed in the previous one, but the approximation was like 2001 with a little decimal point. So it seems like I've taken, let's try 100 instead. Let's approximate this. There we go. If I plug in 100, it's a little bit more, we get a little bit more variation. So 200.98, and if I were to plug in 100 into the 2x plus 1, oh, 2x plus 1, whoops. I get 201, right? And so both of those values should tell you, or should kind of illustrate why the function is below the oblique asymptote at very, very large x values, right? So I picked x equals 100, and I found that the function is just a little bit below the oblique asymptote. So it kind of matches up with my interpretation there, right? This part here, down here, you won't really have to show that. Like if you are dealing with a rational function that has an oblique asymptote, basically you're going to figure out where your function is with your other clues. You won't be using like this clue, okay? So that's about it for me. We've been going for about an hour. Any final thoughts, final questions, or are we good for the weekend?